Whether you're a seasoned 3D printing veteran or an absolute beginner, using an entry-level machine or a high-end industrial one, at some point, you're going to have issues. So in this video, we're gonna look at the top 20 plus most common 3D printing issues, ranging from annoying print quality nonsense all the way to catastrophic failures, to help you understand what causes them and, more importantly, how to fix them fast. Let's get after it. For your convenience, I've broken this video down into sections, which are then further broken down into chapters. We'll go ahead and start the list off with the print bed issues, but as always, feel free to use those chapters down below to skip ahead. Though, who knows, you might just learn something even if you stick around in a section that you think you know all about. The most common issue by far in 3D printing has got to be bed adhesion. After all, for a print to be successful, it has to, stick around long enough for the subsequent layers to be stacked. So if you're experiencing your 3D prints detaching midway through the printing process and creating spaghetti monsters, it is likely that bed adhesion is your issue. Now, this can be caused by a few different things that you will learn to diagnose later on in the video, such as improper Z height. But for now, the first and most important diagnostic step is one that absolutely never hurts. Wash your build plate with a high-quality degreasing dish soap. Now, I've covered this so many times before on the channel, I can't even count, but not all dish soaps are created equal, and it does seem that the brand name versions like Dawn and Palmolive do work much better. You also have to stay away from any dish soap that has aloe or moisturizers or markets itself to be softer on skin. Going forward, it is also a good idea to just avoid touching the build plate as much as possible when removing 3D prints. A clean build plate should solve the majority of detachment issues if you're printing with the kind of normal run-of-the-mill filaments like PLA and PETG, especially with some of these high-grip build plates that are popular on the market today. But sometimes on some designs or with some of the more exotic materials like ABS or nylon, you may still experience either partial or complete detachment. Now, this often shows up as warping. Basically, as the plastic cools and contracts, it wants to shrink, but it doesn't do so evenly. To solve this issue, we have a range of tools in our arsenal. First, we can use something called brims to kind of stick down the edges of the print a little bit more to the build surface. Or, if only some areas are problematic, we can use so-called mouse ears. Additionally, printing in an enclosed or even enclosed and heated chamber should help with some of the more exotic materials and prevent drafts on the less exotic materials. But if neither of those things work, or if you just want a little bit of extra insurance, it is worth investing in a high-quality, dedicated bed adhesive for the materials that you're printing. I've long been a big fan of channel sponsor Magigoo because they have different dedicated formulas for various types of plastics, but many people in the community also swear by 3D Lac or Vision Miner Nano. Now, these adhesives might seem a little bit expensive for what is basically fancy glue, but in my experience, they are well worth it, and they will save you having to worry about bed adhesion or losing prints, especially when you're dealing with those more expensive materials. Another thing that can cause bed adhesion issues is printing a little bit too far away from the bed. For example, 0.1 millimeters too high. Conversely, printing too close to the bed can cause elephant's foot or print defects, or even collisions that cause layer shifts. Of course, most modern printers will automatically calibrate the Z-axis offset, but they are not infallible. Debris on the nozzle or switching build plates can throw these systems off, so it is definitely worth taking the time to learn what too close or too far actually look like. So here are some examples of a print that is too close to the bed, much too close to the bed, too far from the bed, and just right. Go ahead and burn these images into your memory because they will help you diagnose a lot of issues that you'll experience. Unfortunately, some modern 3D printer brands don't really allow you to easily or manually dial in and adjust the offset yourself. And in that case, you will just need to solve whatever the root cause of it is, such as cleaning debris off the nozzle. If, however, you are able to adjust it on your printer, it's usually very easy to do that mid-print. I like to enable brims when I'm not sure if my Z offset is correct, because that gives me an opportunity to adjust the Z offset in real time before the printer actually starts. Another thing that is handled automatically by most modern printers is leveling the bed. Using your software, your printer will probe the bed and then compensate for those imperceptible differences in height as it prints. But this compensation, again, isn't perfect, and it certainly isn't as good as just having the actual bed be actually level. So if you start noticing thin or thicker spots in your print, chances are your bed's not level. Most printers will still allow you to level the bed manually using screws under the bed, and if yours is one of them, you can simply take a piece of paper, like we used to do in the olden days, and adjust each corner until the nozzle drags slightly but lets the paper pass through. Here's a pro tip as well. If your printer is running on Klipper firmware, you can actually see a map of the bed level to see if it's worth doing this step at all. But unfortunately, here again, many manufacturers do not actually offer this functionality anymore. Finally, we have elephant's foot, which looks like this. It's a sort of bulging out of the first layer. Even if you've adjusted your Z offset perfectly, with some build surfaces or materials, this issue can still rear its ugly foot. But fortunately, there is actually a setting built right within your slicer to actually help you fix this very easily. Simply search for elephant's foot compensation and play with the settings till you get it just right. Though I do want to give a quick note here, because this whole issue actually could also be caused by having the bed temperature too high, so check that as well and compare to your manufacturer's recommendation on the filament spool before you go tweaking other settings. After all the bed-related issues, the next most common type of issues both in marriages and in 3D printing is related to extrusion. So let's go ahead and take a look at each of those potential issues. In a second, we're going to get into some of the more esoteric and unusual issues that you might not know about yet. But before we do, let's quickly cover nozzle clogs. Despite the quality of filament being better than ever, nozzle clogs are still a reality in 3D printing. And by the way, not all nozzle clogs are immediately evident. You could, for example, have a partial nozzle clog and not even know it, besides maybe experiencing some under-extrusion, which we're gonna cover in just a moment. Or, for example, filament not extruding out straight from the nozzle when you try to load it. The fastest way to clear a nozzle clog is, of course, with an acupuncture needle, but unfortunately, that's not always the most effective way. For this reason, it's a good idea to learn how to do a cold pull. Now, I've explained this technique before on the channel, and we also created a YouTube short about it, so I'll just link that below so you can check it out. But basically, a cold pull means letting the filament cool down to about 100 degrees Celsius in the nozzle and then pulling it out. Pretty simple. But what if you keep getting nozzle clogs over and over again on a filament that you know to be good? Well, in that case, you're likely dealing with heat creep. Now, allow me to explain what this is. In order to push filament through your hot end, your 3D printer needs a clean separation between the hot area and the cold area. That's why there's a heat sink and a fan right above the heat break. But if this fan gets damaged, filled with gunk, or disconnected, your printer will clog up faster than me on a trip to Hong Kong. To fix this, check or replace the heatsink fan, ensuring that it's providing plenty of airflow over the hot end. Additionally, keep in mind that some enclosed printers do need you to open the door or cover manually when printing PLA or PETG, otherwise the internal temperature can actually get too hot for the fan and heatsink to actually cool properly. Though I am excited to see more and more printers doing this automatically. Another common issue in 3D printing is under-extrusion. You can identify it by little holes or gaps mid-extrusion, especially on long, uninterrupted extrusions. Here's what it looks like. If you see this, your printer is trying to push filament at a faster rate than the hot end can actually melt it. Now, there are a lot of things that can cause this. You could, of course, be printing too fast for the filament that you're actually using. You could have a partial clog, like I mentioned before, or even a slipping extruder gear. Or you could have your temperature settings too low. So first things first, I recommend that you rule out the mechanical issues such as a partial clog or an extruder gear slipping, especially if this is a filament you've used before. Now, if you're sure it's not a mechanical problem, the best way to diagnose this issue is to test the filament's flow rate using the built-in tools in Orca Slicer. Increase the temperature to the maximum suggested by the manufacturer and let her rip. Then adjust the flow rates in your slicing profile and try again. But what if those little gaps aren't actually in the long sections, but instead in corners or seams like this? Well, in that case, your issue isn't max flow rate, but rather something called pressure advance. See, different plastics have different viscosities, and subsequently, they flow differently depending on what's in them and also what the geometry is that they're trying to move through. It's all very complicated stuff, but to account for this, our 3D printers, slicers, and firmware use something called pressure advance, which sort of adjusts the flow in anticipation of slowing down or speeding up. Now, some printers even do this automatically right in the printer by testing out the extrusion before starting a print. If, however, you're still experiencing gaps in things like corners and seams, your printer or your profile is overcompensating with a pressure advance value that's just too high. Like the previous issue, this can be solved by printing out a pressure advance test in OrcaSlicer to get the ideal value for your specific filament. And this is probably something you should do on any new filament you get. For extra credit, you can also print a temperature tower beforehand to then see which temperature is best for that filament before you go on testing other parameters like pressure advance. Just don't forget to save the new values in a new profile, or you're gonna have to do it again every single time. But what if you have the opposite issue? Your corners are rounded and your details look mushy. Well, then that's caused by the opposite miscalibration, a pressure advance value which is too low. Basically, your printer or slicer isn't adequately compensating for the fact that it's going to need to slow down for the corners or small details. And as a result, those details are actually coming out over-extruded in those specific areas. Fortunately, you already know the solution. Just print out a pressure advance test and adjust accordingly. Okay, but what if everywhere on your print is imprecise? For example, if dimensions are not accurate, lines are ugly, and parts are just not fitting together. Well, in that case, you may just be dealing with over-extrusion. Now, admittedly, this one is more rare because most modern slicers have pretty good extrusion multipliers for most of the common filaments, and your printer probably shipped with properly calibrated extruder steps from the factory, unless it's a DIY printer. But as you branch out and try more exotic new filaments, which I highly recommend, you are bound to run into this one eventually, so you should know how to identify it. Now, unfortunately, this one is not as quick and easy to dial in as the others, as there's no definitive test to tell you which values to punch in. A good starting point, though, is to just check the manufacturer's recommendations and to see what the extrusion multiplier is that they suggest. Alternatively, you can look at other similar filament types from other brands and manufacturers in your slicer or from other profiles from other companies to get an idea of which values to start with. From there, you can go ahead and adjust on the go while printing using the flow percentage setting right on your printer. Next up is shrinkage. This is one of those annoying issues where your print looks absolutely perfect, but the moment you try to actually use it, you realize that it's just a tiny bit too small. Maybe a bearing won't fit into a housing or a lid won't snap onto a box. Now, I want to be clear here and specify that we're not just talking about holes being smaller, which is a different thing that's caused by the way your 3D printer actually creates holes and is handled by a different setting in the slicer. Here specifically, I'm talking about everything being just a tiny little bit too small, even straight lines. And the cause of this is just a classic case of physics working against you. Basically, as plastic cools down from its melting point to room temperature, it naturally contracts. Some materials, like PLA, shrink very, very little, usually less than 1%. But more professional or exotic materials like ABS or nylon can shrink significantly more, sometimes up to 2 or even 3%. Now, to fix this, you have a couple of options. The simplest way is to just scale your model up by a tiny bit in the slicer before you hit print. But that only solves the problem once, and if you want to avoid it the next time you go to use that filament, you really should do it the right way. Most modern slicers, like OrcaSlicer, have a specific setting for shrinkage compensation. So by printing a calibration cube and then measuring it carefully with a pair of calipers, you can dial in an exact value that the slicer will then use to automatically offset those dimensions dimensions in the future for you. It takes an extra 5 minutes of calibration, but it will definitely save you from the frustration of reprinting parts that just don't fit. Or, of course, you can always look around at other companies' profiles and use that as a starting point. Just make sure to actually save these values in a custom filament profile so you have it ready for next time. Perhaps the most common extrusion-related issue is oozing or stringing, basically prints that look like this. There are a few different things that could actually cause this. First, your temperature might just be too high, so consider printing a temperature tower like the one we mentioned before. Second, your retraction distances might be off, meaning that your printer is retracting either too much or too little when moving between extrusions. Now here, once again, there is a built-in test right in OrcaSlicer to actually help you dial that in. And finally, it might be your filament itself. See, all plastics absorb water, but some do it much more than others. It's called being hygroscopic. PETG and TPU, for example, are notorious for doing this. So it never hurts to dry your filament using a filament dryer before you start printing. But here's how to test if it's actually necessary and if the problem is actually caused by moisture in your filament. Simply raise the nozzle up high enough that you can see under it and then load filament and extrude. If you hear any popping or see any bubbling, then congratulations, your filament has soaked up water. So dry it according to this table and try again. If all else fails, you can also play with travel speeds or enable the avoid crossing perimeters feature as a last resort, rather than actually solving the problem itself. But what if some parts of the print look fine, but details just aren't that crisp anymore? They're not consistently bad in any specific way or area like they were when we talked about Pressure Advance. They're just kind of not clean anymore. Well, this one is much harder to diagnose because it could be the print speed or issues with the motion system, which we're going to cover in a whole section up next. But it also could be a worn out nozzle. 3D printing nozzles are considered a consumable, and they can wear out very, very quickly with today's carbon and glass-filled composites. Now, this issue can go unnoticed for a very long time because it is a slow and almost imperceptible decline in quality over time. Kind of like how you don't notice yourself aging unless you upload 4K videos of yourself to YouTube and go, God, what happened? To rule this issue out, simply remove your nozzle, clean it, and look down the business end. If it's not circular or the circle looks bigger than a new nozzle, which you hopefully have on hand, go ahead and replace it. Problem solved. So we've covered ugly details, ugly bottom layers, ugly large patches, but what if your top surfaces are ugly? In a way, this is similar to over-extrusion, but it is isolated to the top layer. Fortunately, it's for this exact reason that our slicers give us more granular control over that top layer. First, we are able to adjust the extrusion width of our top layer, dialing it down to be finer or thicker. Next, we can slow down the top layers so they print at a higher quality. Third, you can add more top layers in hopes of smoothing over those imperfections. And finally, we have the option to extrude only one perimeter on the top layer. And this can make a huge difference in the finished look of the print because on the top layer, we simply don't have the print surface to squish the layers together and create a nice uniform surface. If, however, you do want to achieve that look or close to it on both the top and bottom layers, you will need to look into a feature called ironing. This is where the printer goes back over a top-facing surface, extruding a tiny amount of plastic to try and fill in the gaps between the lines. It takes a ton of time to do this, and it's really hard to get right without doing extensive calibration. But if your application requires silky smooth top layers and you're not interested in sanding them because who likes to sand, then this is the way to go. And finally, one more extrusion-related issue before we move on to the cooling-related problems. A lot of times, supports are a necessary evil in 3D printing, but they shouldn't be an absolute nightmare to remove. If your supports are binding to the material in a way that is either leaving scars or making it difficult for you to remove them, then you have a few options. It might be insufficient cooling, which we're going to cover in its own entire section up next, but it may be as simple as just adjusting the settings. You do have a wide range of settings at your disposal in the slicer, including the distance between the supports and your print, the number of interface layers, and even more granular settings that control the spacing between the extrusions on the actual interface layers. You can even control the speed at which supports are printed. But to be honest with you guys, you shouldn't have to play too much with any of this. Generally, especially if you have good profiles from your 3D printer manufacturer, most of the time, just slightly increasing the support distance, slowing down support printing speed, or adding an extra interface layer should be enough to make support removal an absolute breeze for most materials. But because there are so many different variables at play here and so many different materials out there, you really will just have to borrow from readily available profiles and experiment till you find something that works well for you. Dang, 3D printing seems super hard. There are just so many little things that can get messed up or totally screw up your print. I mean, yeah, but honestly, you can avoid like 80% of these issues by just choosing a high quality 3D printer from a company that rigorously tests their hardware, their software, and their profiles. Huh, I guess you're right. A lot of that stuff does come down to calibration, and I kind of would expect my 3D printer manufacturer to provide that kind of stuff for me, right? Ugh, I know, right? It's honestly like one of my major pet peeves with 3D printer manufacturers. It's also why I mostly run Prusa machines in my own shop and print farm. Prusa? Aren't they like really expensive? I mean, yeah, you pay a bit more than some of the machines on the market, but in exchange, you get a lot. You get a machine that is gonna last you a lifetime with an upgrade path every time they come out with a new machine rather than expecting you to buy a new one. Plus, you get 24/7 customer support and you get guaranteed security, open source hardware and firmware, and just a complete ecosystem of software, slicer, filaments that work with it. Plus, you're supporting a company that actually gives back to the 3D printing community rather than just taking all the time. I'm in an advertisement again, aren't I? Oh yeah, but I do mean literally every single word I said. And there is a link in the description if you want to support the channel, as well as the sponsors that make these videos possible. I really can't wait for AI to replace all these influencers. All right, we have covered bed issues and extrusion issues. Now let's talk about issues stemming from cooling. Cooling is a little bit simpler than the other types of issues that we've been looking into in this video because really there can only be either too much cooling or too little. So I'm gonna go ahead and go through these ones a little bit quicker, showing you what they look like and which of the two causes them. Our first cooling related issue is bad layer adhesion. To be fair, this can be caused by printing too fast or at too low of a temperature as well. Now with more exotic materials, it can also be caused by printing in too cold of an environment. But the bottom line here is that this issue is ultimately caused by the individual beads of plastic of two separate layers just not being warm enough when they are bonded together. Now, if you're reasonably confident that you're printing at the right temperature and you haven't selected the wrong profile, for example, and you aren't printing at unreasonably high speeds or flow rates, or in a particularly cold environment, then most likely your cooling is just too high. Now this would cause the material to actually cool too fast before it even gets a chance to properly bond to the layer before it. This can happen if you're coming from printing mostly PETG and PLA, which love as much cooling as they can possibly get, to now printing ABS, nylon, or even polycarbonate, which prefer to have as little cooling as possible. Adjust cooling down, but not so low that you can't successfully print bridges or overhangs. And that's a great segue into ugly overhangs and bridges. As you probably know, while we can print bridges or moderate overhangs of say 45 degrees, a 3D printer just cannot print a cantilever into mid-air. But if you are experiencing issues with either bridging or overhangs, such as sagging, then insufficient cooling is probably your issue. However, this one is a little bit tricky because you might find that your cooling fan is already set to 100% for bridges and overhangs, only to find that the result is still not satisfactory. You might even have the slow down feature set in your slicer and still the results are mid at best. If this is the case, it is likely that the issue also has to do with the direction of the cooling vent. While some 3D printers do offer 360-degree cooling, like those from this video's sponsor, Prusa, others do have a very directional airflow on the part cooling fan vent. Now, some printer manufacturers have solved this by adding auxiliary fans to the housing of the printer. For you, there are a few ways to fix this. One is very quick, and another one is more complicated. The quick fix is to just try and rotate the part so that any overhangs are facing either the part cooling fan vent or the auxiliary fan. Over time and through experience, you will get to know in which direction your various printer or printers offer the best cooling, and then you can plan accordingly. The other fix is to obviously upgrade your cooling. There are all sorts of modifications out there, ranging from tiny tweaks for your specific printer to entire new toolhead designs or even add-on auxiliary fans. So if you're going to be printing lots of bridges and overhangs, particularly on materials like PLA and PETG, it can be worth investing in some of those upgrades. Here's a common issue that I see on a lot of entry-level 3D printers: pillowing. This is where the top layers sag or droop over the infill rather than properly bridging. In a way, it's kind of the same as poor bridging, you just don't have enough cooling to bridge properly. But unlike in that instance, this one can be solved with a simple setting rather than a physical upgrade. If increasing the fan speed is no longer an option, just add an additional top layer or two to cover up this imperfection. We have finally arrived at our final section in the video, the motion-related issues. Now, the first, most common and most disappointing motion-related issue has got to be the notorious layer shift. This is when your printer skips steps in either X or Y and continues printing, just in the wrong place. I saved this one for much later in the video because, frustratingly, there can be a lot of reasons for layer shifts, many of which we have already covered. You could, for example, have over-extrusion issues which are causing the nozzle to collide. You could be printing too fast. You could have a cooling issue that is causing layers to curl up, or perhaps your Z-hop, the setting that lifts the nozzle up to avoid colliding with the print, is set too low or too fast. Fortunately, there are tests available in OrcaSlicer to test and refine most of these settings, so that's a good place to start. But layer shifts can be caused by more serious issues as well. These include improperly tensioned belts, debris in your idler pulleys, insufficient lubrication, an obstruction in the path of the toolhead or filament, or even damaged bearings. So if adjusting speeds, cooling, extrusion multiplier, and Z-hop settings just don't resolve your issue, try disabling the motors of your printer and moving the toolhead around the full range of motion. Try to feel for any areas of resistance or friction, or see where a collision might be occurring. If everything seems fine, then it is likely print speeds or belt tension. So let's cover that next in our section on ghosting and ringing. Because of the way 3D printers work, some ghosting or ringing is inevitable. But if you are experiencing more than what is considered normal, for example, these prints that you're seeing on screen, there can be a few different causes. The first thing to check is going to be belt tension. Over time, your 3D printer's belts can get out of whack, which will cause vibrations and imprecise movements. Some companies do publish guides on how to tension the belts of their specific printers, while others suggest tools to measure the belt tension. Still others, like Prusa, actually include a useful tool right in their smartphone app to get belt tension just right. Now, it's worth checking your belt tension at least every few months just to ensure that your printer is still running optimally. If belt tension is dialed in and you're still experiencing issues, it's then time to look into resonance compensation. This is where your 3D printer measures the resonance frequencies in each axis and compensates for them when sending movement commands. Many printers today do this automatically, either during setup or before every single print. Now, if yours doesn't, you can usually manually initiate a measurement and save the new values. And even if your printer doesn't have a built-in accelerometer on the toolhead, you can actually buy an external one for printers that run on Klipper, or even from Prusa if you have one of their printers. Now, this step will be necessary if you've changed something on your toolhead or motion system that would cause resonances to deviate from the originals, such as adding weight or changing where weight sits. Finally, we have Z-banding, which is one of the most frustrating aesthetic issues because it can be so persistent. You can identify it by consistent, repeating horizontal lines or ribs that appear all the way up the vertical walls of your 3D print. Unlike a random layer shift, this is a rhythmic pattern that makes your smooth surfaces look kind of like a topographical map. There are usually two main culprits for this. The first is mechanical, typically involving your Z-axis lead screw. If that rod is even slightly bent, or if the nut that moves it up and down is binding, it will cause the nozzle to wobble in a repeating pattern as the gantry climbs. To fix this, start by making sure that your lead screw is clean and properly lubricated. You should also check the coupler that attaches the motor to the rod. If it's loose or misaligned, it is going to cause issues. The second cause, and one that people often miss, is actually thermal. If your bed or hot end temperature is fluctuating wildly during the print, the plastic expands and contracts at different rates, creating those visible bands. The fix for this is called PID tuning. Most modern printers have a calibration tool for this right in the menu. It essentially teaches your printer how to maintain a rock-solid temperature, which can often smooth out those walls instantly. By the way, if you've enjoyed this video, it was honestly a lot of work to put together, so it would really mean the world to me and the team if you took a second to just like the video and let us know in the comments down below if you learned something. Additionally, if this kind of video is your thing, then you should definitely hit that subscribe button, because this is the kind of stuff that we put out nearly every single week around here. In fact, we recently put out a video just like this one, sharing about a dozen of the most useful but little known hacks and workarounds to just greatly improve your 3D printing workflow. If you like this video, you're definitely gonna love that one, so I will go ahead and link it somewhere on the screen right now. That's all for this week, but I'll see all of you on the next layer.